Hi. Now that we've covered the main assumptions of the Solow growth model, we can move on to actually building the model itself. Okay, so just what did we say this for? We had that production per effective worker is some function of capital per effective worker, and we know that first derivative of this function is positive, while the second is negative. We also assumed that state of technology as well as labor are growing at constant rates given by rho and lambda respectively. Okay, but now we need to demonstrate how the economy is behaving. Because, of course, from macroeconomics class, you know relationship between savings and investment, where do we get the savings? Then, but how does it work? Look, let's start with output. Now, if we know how much output we've got, so how much been produced, we will be able to determine the level of savings. So, in our example, in our model, we want to make this very, very simple. So, we're going to assume that economic agents are saving a constant portion of output. So, this lowercase s that you see over here is the savings rate. And of course, this s needs to be somewhere between 0 and 1. And this is the portion of GDP that the occupants of our models of economic agents living within this model are saving. Now, the next thing we know is that in equilibrium, savings through the magic of financial markets are transferred into investment, right? So, investment, of course, are purchases of capital goods in the economy, right? So, if we have investment, then this will induce a change in the level of capital. And look, now, the bigger the amount of capital in the economy we've got, the bigger is going to be the level of output. And look, bigger the level of output, bigger the savings, bigger the investment, bigger the change in the level of capital, bigger the GDP, and so forth. But of course, there is one tiny detail that we are missing over here. Okay, so what is this tiny detail? Let's think for a second about change in the level of capital in the economy. So K with the dot, of course, is by definition derivative of K with respect to time. Now, this should be equal, or at least determined, by the level of investment at time t, right? But I hope you remember from our previous considerations that saying investment sometimes is enough, but we would like to know whether we are talking about net or gross investment. Look, what we see over here, change in the level of capital is actually net investment. Right? Over here, what we have over here is associated with this graph, right? We've got savings are determining the level of investment. Investments are purchases of capital goods by companies, right? So, in this case, what we have over here are gross investments. So those are all those purchases. Okay, so if we want to go from gross investments to net investments, what else should we have here? Well, we need to account for depreciation, because it's obvious that if we use the capital, it loses its value. Like when you drive a car, of course, with age, it's being worth less and less. And the same, of course, is with capital. So before we can actually obtain net investment, we need to subtract from gross investments depreciation. Now, what is depreciation? Well, this is the loss in the value of capital that we already have. So, look here, we can start with having some level of capital. We know that part of it is going to be deteriorated, used up. How much? Let's just say, for simplicity, that this part is given by a percentage of the value of this entire capital, or denoted by delta. And delta, over here, is depreciation rate. Again, as delta is a rate, so it's not a rat, because of course it's a rate. Delta must be somewhere between 0 and 1, right? So delta informs us about what is the percentage of the capital that has been used in the economy and lost due to this usage. And look, now if I subtract depreciation from gross investment, I'm going to get actual change in the level of capital in the economy. So look, going back to this graph, here we need to make this correction for depreciation. And basically, if we didn't have any depreciation, of course our capital would be growing faster. But, of course, this puts a little bit of a brake on the growth rate of the stock of the capital, and due to that, actually our GDP is increasing a little bit slower. Okay, usually, how much is this depreciation rate? Usually depends on the economy, but 10% is a good estimate. Okay, but then from this moment on, we can actually start using the graph from over here to get a better and better description of net investment. So, first, we can replace investment with savings, because we know that they're going to be equal to 1. Then, again, we've assumed that economic agents are saving constant portion of the GDP. So I can replace savings with savings rate times Q, and now with minus minus delta K of T. Okay, and this is the expression we can actually work with. Okay, so we clearly see that this expression and this expression are the same. But let's work with them a little bit more. Okay, so we've got changing the level of capital or net investment is equal to savings rate times Q. I'm going to be dropping the Q subscript, I'm sorry, the T from the functions because it's going to make things too long unnecessarily, minus delta K. Okay, but now look, remember what we've assumed at the very beginning. We've actually developed a relationship between production per effective worker and capital per effective worker. So out of this, we can get that Q could be replaced if I multiply both sides of this equation by AL times V of lower, I hope everybody can see that this is lowercase k, so capital per effective worker. So let's do this. Let's do this over here. Okay, so we've got that net investment is equal to S times AL times V of K. Okay, and how about capital? Like, we don't want this expression with capital over here. Can we somehow get rid of it? Well, there is a very simple trick to this as well. But I'm going to do it in the following way. Please remember that capital per effective worker is given by this formula. So look, from this I can calculate that capital must be equal to AL times lowercase k, right? I just multiply both sides by this. Now I can replace expression for capital by this expression we've got over here. So we've got that this is minus delta AL lowercase k. Okay, and look, we have actually accomplished quite a lot at this moment because we have expressed net investment in the economy as a function of capital per effective worker and some other things. So state of the technology, labor, depreciation rate, and savings rate. Right? Okay. So now, what should we do next? Look, now we need to just do one very simple mathematical trick. Okay, and before we go on to this trick, let me remind you of very simple things from mathematics that we use actually very often. Look, when we had a situation when we needed to calculate derivative, okay, let's just say with respect to time, out of product of some function of time times some other function of time. We used the product rule. And look, the product rule stated that this is f prime of t times g of t plus f of t times g prime of t. Okay, I hope this everybody knows very, very well. But this rule can be easily extended, and actually this is what we've proven during our mathematics class, that to the case of 3, 4, 5, or 7 components in the product. So now look, if I would have derivative with respect to time again of f of t times g of t times h of t, what I'm going to get out of it? I'm going to get that this is going to be f prime of t times g of t times h of t plus t times g prime of t times h of t and plus f of t times g of t times h prime of t. Okay, so you see, we basically get exactly the same expression as the one that we had over here, but 3 times, and here we have a derivative, here we have a derivative, here we have a derivative. Okay, the proof and general explanation of this formula you can find in the link in the description of the video. Now, we can quite easily utilize this to rewrite a change in capital, but in a little bit different form. Okay, so remember that net investment, so change in level of capital, is nothing more than the first derivative of capital with respect to time. Right? This is the expression we've got over here. And look, using this expression that we've got over here, we can differentiate capital as a function, as a product of state of technology, labor force, and capital per effective work. Okay, so look, let's go back over here. We remember that this is a derivative of capital with respect to time. So, in other words, what we are doing over here is, by definition, we are calculating derivative with respect to time of the expression A, L, lowercase k. Right? So, how do we do it? Look, we're just going to use this formula, but instead of using primes, we're going to be using dots. So, what should we get here? This is equal to A with a dot, L, K, plus A, L with a dot, so this derivative with respect to time times K, plus A, L, K, with a dot. Okay, so now that we've obtained this outcome, maybe we can work a little bit with it, right? Because look, what we don't like over here are the expressions A with the dot and L with the dot. How can I get rid of them? Okay, this is also not a very complicated thing to do. We can use the relationship that we assumed at the very beginning. Because look, growth rate of state of technology is given by A with the dot divided by A, which means that A with the dot is equal to rho times A. And by the same token, change in level of labor is given by growth rate of labor times labor. And now I can use those two relationships and substitute them into the equation for net investment. Okay, so I get that change in the level of capital is given by rho A L K plus lambda A L K plus L A K with a dot. Lowercase k, of course. And look, what have we accomplished right now? Well, I hope you can see that we expressed net investment in a different way, but because this is expression for net investment, and this is an expression for net investment, they need to be equal to one another. Okay, so let's compare them by sides. Okay, let me just do it over here. Because we don't need this anymore. We've got all the information from that entire model already contained in those two equations that will become one in a second. And this is actually what I'm going to do. I'm going to compare this equation with this equation. So I get that rho ALK plus lambda ALK, but of course lowercase k, plus, so capital per effective worker, AL, capital per effective worker with a dot, so change of it over time, times SAL, phi of lowercase k minus lambda ALK. Okay, and look, I hope you can readily see that there's something we can get rid of. It's AL. AL is in every expression, so if I divide both sides by AL, it's gone. Okay, so what now do we have here? So we've got rho times k plus lambda times k plus k with a dot s phi k minus delta k. Okay, let's organize those expressions. So look, I can, for example, subtract those two expressions from both sides. So I'm going to get the change in the level of capital per effective worker is equal to S times phi of k minus rho k minus lambda k minus delta k. Right? Now you can clearly see that k is repeated here 3 times, so why not take it out of the parentheses? And we end up with k equal to S times phi of k minus rho plus lambda plus delta k. And look, what you see over here is the main equation. This is the engine of Solow growth model. Because this is our law of motion. This equation is actually describing to us how capital per worker in this simple economy is changing over time. And look, we see that here it will depend on 2 things. On one hand, we will have this first expression, like connected with the phi, so function of the production per effective worker, and the second part associated with the state, the level of capital per effective worker, plus this coefficient associated with technological progress growth, labor force growth, and depreciation. Okay, now, as we do not know exact form of this function, right, it's in general form, we cannot solve it directly. So, what we're going to do is that we're going to try to solve it using a graph. Okay, so let's do it. Okay, first, let's start with what we already know. Okay, what we already know is that the function in which output per effective worker is related to capital per effective worker looks like that. So here is the function phi of capital per effective work. But look, what we've got in this equation is something different. This is S times phi of k. But what was S? S, remember, I hope you remember, is the savings rate, because this is lowercase s. So this is some number between 0 and 1. Usually thinking about it as between 0.1 and 0.5 is the best rule of thumb, depending of course on the different economies, but that's a really good estimate. Okay, so what does it imply for us? Look, this implies that out of this function, we only need to take a certain portion. So what are we going to end up with? Well, we're going to end up with the function with similar shape just being a little bit lower. Because look, we always get simply, assuming for example that S is 20%, so 0.2, we've got 0.2 of that, 0.2 of that, 0.2 of that, 0.2 of that, 0.2 of that. I hope you get the idea. Okay, so this is going to be the first part of the model. Okay, so let's draw this model over here. So we already have the first part. Okay, so here is going to be key, capital per effective worker. Here we have output per effective worker. So we get the first part. So the savings per effective worker. Okay, so here we have this S times P of K. Okay. So now that we have this, we need to take care of the second part of this equation. Look, the second part of this equation is here. And look, again, it is related to k. And look, this is a linear function. If I differentiate this expression with respect to k, I'm going to get minus rho plus lambda plus delta. Okay, but this minus is unnecessary for us. We're going to just use this part. And I'm going to draw it now on the graph. So here I'm going to use simple linear function with the slope given by the sum of rho, so technological progress, growth rate of population, and depreciation rate. So we've got rho plus lambda plus delta times capital per effective worker. Okay, so I think we're ready to finally establish what is happening in this economy. Okay, now let me use, because here we will have different possible cases of what is happening, so let me use just 2 blackboards for that. And let's first, look, everything we do here is governed by this equation. But let's see what is happening at the different parts. Okay, and clearly we have 3 possible cases over here. Look, over here we see that savings per effective worker are bigger than this expression. So capital per effective worker multiplied by rho plus lambda plus delta. So what does this imply for us? Let's just say that we are starting that the level of capital per effective worker in the economy at the beginning is somewhere over here. Right? So what do we see over here, we see that this much are the gross investment per effective worker. And here's this function showing us 3 different sources of the decline in capital per effective worker. But you might say, like, okay, I understand that depreciation decreases capital. But why the hell so increasing technology decreases capital per effective worker? Let's go back for a second to a definition of capital per effective worker. Look, here we said that capital per effective worker is equal to capital divided by A and L. So look, actually, here we have 3 different sources of decline in capital per effective worker. Firstly, of course, is depreciation. If we have depreciation hits capital and it becomes smaller. And as a result, capital per effective worker drops. Now, when we talk about AL, when we look at the definition, it also becomes self-explanatory. Look, because when we talk about capital per effective worker, we are dividing by AL. So the better is the state of technology, and the higher is the labor force, the lower will be capital per effective worker. Okay, I know that this might be not very intuitive, like why actually looking at this, why to look at this, but believe me, a couple of minutes and it will become self-evident, like looking at this expression was a brilliant idea and how well it describes how economy is behaving in the long run. Okay, so let's go back to the situation when we are over here. Okay, so we see here clearly that investment per effective worker here is higher than the expression for that. So, like expression that is telling us what declines, what diminishes capital per effective worker. Now let's look at this situation from the other side. So what would happen, for example, if we started at this level of capital? We clearly now see that expression diminishing capital per effective worker is bigger than gross investment per effective worker. Okay, so let's put this our knowledge to a good use. Okay, we clearly see here that to the left of the intercept, we've got a situation when S times phi of k is bigger than rho plus lambda plus delta k. What does it imply? Look, it means that this expression is bigger than this one. So, change in level of capital per effective worker must be positive. But this means, of course, that capital per effective worker is growing. So look, over here we will see that level of capital per effective worker is going to be growing. And what does this imply? Look, it implies that we are moving to the right. And we are moving along this line. And you see, I hope you can see over here, that everywhere over here, investment gross investment per effective worker is bigger. So this implies growth of capital per effective worker. Okay, now what happens to the left? Well, to the left, we've got the opposite situation. So investment, gross investment per effective worker, is lower. So here change in the level of capital per effective worker must be negative. What does this imply? Capital per effective worker needs to be declining. Okay, so now I hope you see that if we're going to start from any point to the right of this intercept, level of capital per effective worker in the economy is going to be declining. So we will move along these lines over here. Okay, and having already discussed the properties of dynamic properties of some differential equations, I hope you can clearly see now where am I going with this. Look, it doesn't really matter at which point over here we're going to start. We always are going to end up at this point. And this point is called a steady state. It's k, of course, lowercase k with a dash. And this is the level of capital per effective worker where economy is moving towards in the long run. Because look, what is so specific about this particular point? Look, at this particular point, we've got that level of gross investment per effective worker is exactly equal to this diminishing expression, which implies capital per effective worker stops growing, so the growth rate, so capital per effective worker stays constant. We've got this point, and we call it, this point, we call the steady state. So regardless of where have we started, we're gonna end up at this point. And look, there's all the forces, economic forces, are driving us back to this point. And once we reach it, there's no reason for getting out of it unless, of course, there is some exogenous change. The example of this exogenous change we're going to discuss in a second. Okay. Look, so now we see where economy is going in the long run. But look, we can actually show this in a simpler way. Why? Look, in 2 videos ago, we were discussing phase diagrams. What is a phase diagram? Phase diagram is phase diagram is a plot of for the differential equation when we have a case that we have dy dt expressed as a function of y alone. And what is this? Look, this is derivative of k with respect to time expressed as a function of k alone. So why not use it and graph it in an even easier way in order to find the steady state? How would we do it? Look, so now what we need to do is to plot on this axis change in capital per effective worker, and on this axis capital per effective worker. Okay, and look, of course, again, we're gonna start over here because we are assuming that if we have zero level of output, zero level of capital per effective worker, we're not producing anything. If we are not producing anything, we don't have anything to save. We don't have anything to save. Nothing is changed. Because of course, if we do not have capital to begin with, there's nothing to depreciate. Okay, so how do we build this phase diagram? It's actually very, very easy because look, we already have all the components of its behavior on a blackboard. Look, here we need to simply devise where this expression is positive, where it's negative, and where it is equal to 0. Right? But we already did that, right? Over here. So what should we do to put it on a phase diagram? Imagine it like that. Let's just say that I'm going to take this line and I'm going to rotate it clockwise, like that. And let's just say that this gross investment per effective worker is glued to this line and it's going along with it. And I'm moving all of this, so this is moving like that, until this line corresponds to horizontal axis. How will it look right now? Well, it will look like something like that. Right? Look, here we see exactly the same relationships as before. Look, here we see that the bigger the capital, in this part, with the bigger capital is associated with positive change. So capital per effective worker is associated with positive change in the level of capital. So we are moving along this line towards the equilibrium point over here, just like we have described with the blue color. Now here we have the yellow colored part, right? Because here we see that for very big, let's just say like that, for big levels of capital per effective worker, change in capital per effective worker is negative. So it must be declining. And again, at this point, we have the steady state. And this is where the model always converges. Okay, so now that we found a steady state, what does it really mean? Look, what is so specific about this steady state? In this steady state, nothing is changing. So you might ask, why do we even interested in it? Like why is it so important to find a state where economy is not growing? But actually, we haven't said that economy here is not growing. What we said is that capital per effective worker is not growing. And this brings us to the amazing conclusions that we are actually getting directly from Solow's growth model. Okay, so let me just just restate what we've got over here. Look, we get from this model that when we get to this level of capital, economy has also steady state level of production per effective worker, right? So what does it imply? It means that it stays the same, it stays constant, it's not changing. But it doesn't mean that the economy is not moving. Okay, look, what can if this is not changing, then we can say that growth rate of output per effective worker is equal to how much? Is equal, of course, to 0. And this information is very valuable. Why? Because we have already learned a couple of things about growth rates. For example, I hope you remember that if y is equal to a times b, then growth rate of y is equal to growth rate of a plus growth rate of b. Yeah, we proved this using logarithms. But we also say that, let's just say that x is equal to c over d, then growth rate of x is equal to growth rate of c minus growth rate of d. Let's use our knowledge about it over here. Okay, so look, if I know this, that this is growth rate of output per effective worker, then I also have that this must be equal to growth rate of output minus growth rate of effective labor, and it's equal to 0, right? But let's go further. Growth rate of output minus growth rate of effective labor is the same as growth rate of state of technology plus growth rate of labor. So we get out of this that growth rate of output in our economy minus growth rate of the state of technology minus growth rate of labor is equal to 0. Because remember, this is what we said before. We divide by AL. This is why this relationship holds. And now look what happens. We learn out of this that growth rate of output, of course, is equal to growth rate of the state of technology plus growth rate of labor. And this conclusion is extremely important one. Why? Look, it tells us that in the steady state, so when we are over here, the economy grows at a rate equal to the sum of growth rate of technology plus growth rate of labor force. But this is not the most important thing, because look, I can work with this expression even further. And what will I say? Look, out of this, I'm getting that growth rate. If I'm going to move this expression over here, I'm going to get growth rate of output minus growth rate of labor force is equal to growth rate of state of technology. Now, what is this? This is simply growth rate of output per worker. This is also growth rate of productivity. And under the assumption that L is generally denoting number of people in the economy, this is growth rate of GDP per capita. So look, this is a measure of the effectiveness of the well-being of the economy. And we see that in the steady state, in the long run, this well-being of the economy is driven purely by technological progress. So in the long run, technological progress is the driving force of the economy. So if we take care of the fact that if we promote policies that are aimed at promoting technological progress, but of course, in terms of technological progress, remember, is very wide here. We can also put human capital, so education, skills possessed by workers. We can expect that our economy is going to be growing faster. And this is the main conclusion, the main idea you should remember from the Solow growth model. That in the long run, in the steady state, technological progress is what makes our lives better. Okay, I know I've probably been talking for too long anyway. I just wanted to show you one last thing. That look, the same trick that I did here with output could be done for level of capital. So if I just replace here with K, with K, with K, with K, with K, with K, and with K here and here, look what do we see? Like, let's just get to this one. Like, capital per worker, which is very important thing in the economy, because this tells us also how productive workers are. But look, again, capital per worker is driven in the long run solely by growth rate of technological progress. So I hope you're going to take the most important lesson from that. And this lesson is that in the long run, technological progress, human capital, so also education, are the main things that can lead to the improvement of our lives. Okay, thank you for your attention and see you in the next video.